This is a special edition video concentrating on how to do homework 2 because homework 2 will be due pretty soon, so I'm going to have to give you a lot of information so you can get it done correctly. So here's the statement of the problem. As I mentioned earlier, you're going to have the accelerometer and the gyro interface to a scope, and the accelerometer is putting out accelerometer data in the X, Y, and Z directions. The gyro is doing the same. You're going to construct switches that are going to allow me to do the following. At any given time, I can select one of the accelerometer axes and one of the ones coming from the gyro. So let's say AX and omega X. Then by throwing the switches, I can change it. Let's say I want to change it at this particular time to the green curve here. And the green curve is indicating what's going on with the y-axis accelerometer acceleration and the gyro. Okay, so this is the plan. So what I want to do here is dig into exploring some of these switches. Then we're going to let our speaker from MathWorks talk us through how to build this system. And so we'll begin right here with our Simulink block. So I gave you this address. This will tell you what all the different components of Simulink that are possible. And on the link from that earlier email, I indicated to look at the section called Signal Attributes. So I want to point out the ones that we're going to look at yet. Actually, it's signal routing. So I want to point out ones that we're going to look at here. The demultiplexer, the multiplexer, the manual switch, the switch, and the multiport switch. Okay, so let's go ahead, go to the manual switch. Okay, so this is the one that you, I believe is the same one that you used on the homework number 1. So as you click it, it will flip from the bottom to the top and make the switch. So let's go back to where we were. Okay, the regular switch is similar to the manual switch, except it's not alterable by touching. So let's continue on to the multiport switch. So the multiport switch is shown here. This one allows me, in this particular case, to make a connection between as many inputs as you want. This one here shows 3, and it's controlled by a switch input number 1. And so here's some examples. This particular one is set up to handle 3 inputs. This one here is set up to handle 4 inputs, and that is controlled by whatever that you put in here. So if you put in the number 2 here, it's going to connect up the second one to the output. I recommend using the multiport switch for the homework that you're using, that you're developing. And now let's take a look at something else that we need to look at. And so let's kind of review what again that we have as we get to signal routing. So we are looking at this device. Well, they call this a demultiplexer. So you put data in and you get data coming out on 3 parts. The fact is, this should bother you, especially if you're a computer engineer. There's no select lines. So this is a Simulink invention, and so let's dig in and see how it works. Demux. So here's a picture from 1 in and 2 out. I think I'll go ahead and go to some examples here. So here's an example. Let's say that you're putting in 6 numbers, and you want, they're all coming in parallel, and I want to distribute 2 over here, 2 over here, and 2 over here. As you can see, this is what's happened. So here's another example showing a different number being distributed to each port. So again, there's no select line. There's nothing telling it how to do it, except that you configure this in advance and it tells you what to do. In your case, you're going to do 1, 1, 1 because you're going to have 3 elements streaming, and you're going to have data streaming in here in having 3 elements here, and then you're going to distribute each one to each port. Okay, so I think that concludes what I wanted to discuss from this sheet. Let's go back here. So in this particular case, I'm going to have you decide how to do this. The switches should simultaneously go from the X to the Y to the Z. So therefore, you should have both of these switches controlled by the same input. So they simultaneously switch. Now, let's go ahead and take a look at the discussion for this homework. It begins at 14:10, but we're going to rewind to the beginning of the video. And this is the video here. And we're going to watch to see how this thing is developed in terms of just blinking a light. Okay, so if we can understand how to set up the Arduino to blink a light, then we can move into this more complicated scenario. So our presenter is talking right now, and she is about ready to lay some elements on the palette here. So let's listen in and see what she's doing.
You can simply drag and drop them. You could also type on the Simulink window to get a block. The first demo that I will be showing you is for digital input-output. The first thing you need to do is configure your model. For that, go to Model Configuration Parameters. Search for the Hardware Implementation option. Choose the hardware board.
Now, we are using the 2500, the 2560 for most of you. I think some of you have a DO, so you'll switch over to that. All right. Basically, the difference between these depend upon the speed of the processor. The Mega 2560 and the UNA are essentially identical, except that the 2560 has a lot more input and output ports. The DO runs at 84 megahertz, as opposed to the Mega and the UNO, which run at 16 megahertz. And some of these other options have also Wi-Fi and some other things. So there's a variety of choices to make. But your kit, you're provided with a kit, so most of you have the Mega 2560.
In my case, I'm using an Arduino Mega 2560. Go to Target Hardware Resources, go to Simulink IO, and check the Simulink IO option. Right now, it's already checked. So I will be demonstrating the blinking of an LED using the digital output block. I'll do it in 2 ways. One is automatically using the pulse generator block, and the other is manually using the manual switch block.
We will just do the first
case. So let's do the first thing. Take a pulse generator block and a digital output block. Connect these two. Set the pin number in the digital output block to 13, since that is the LED on this board. You can also go to the pulse generator block and set the various parameters.
Now 50% pulse width would mean that it's on, in this case, for 3 seconds and off for 3 seconds. But you can set that to whatever you want. Now, before she goes any further, let me explain the setup. We're using Simulink IO. What happens is that the PC will download a server to the Arduino board. That Arduino board then has communication between the PC and itself. This represents the actual pin 13. Pin 13 is connected to an internal LED on the Arduino Mega. If you use a different pin number, it won't work. The pulse generator, on the other hand, is in the PC. Between the two, between this communication link is essentially reflecting the server. Whatever you tell it to do on the PC, it will reflect itself into the Arduino. This is actual hardware. This is your software that you're running. So that is beautiful for simulation purposes. Now, if you actually desire to make this a permanent thing, you would disconnect this server and then download the hard code into the Arduino, and it'll do the same thing.
Next, we need to go to the pacing options. So Simulink Pacer basically tells your Simulink model how fast it is supposed to run as compared to real time. Right now I have set it to 1. Let's try running the model. You can see the blinking of the LED. It is on for 50% of the period and off for the other 50%.
I might mention here before she goes any further, in between the time that she pushed that button and got a result here, the server was downloaded. But this was already done by her at an earlier time. It will take at least a minute to download that server into the Arduino. So don't expect it to respond as quickly as it just did. It will afterwards. Once you have the server there, it will be very fast. But this was not realistic.
The period is set to 6. Next.
Okay, so the next for us will be looking at something different. We're going to go all the way to the IMU example, which is at 1410. And by the way, she has several examples here, so we are, very, very happy to be able to have that. So let's take a look to see what we're doing here. Again, we are setting this up. Now I'm going to talk about the construction of this side here. So just to review from what we discussed last time, we are going to build a system, all right, that is going to incorporate some registers. So you'll see where I'll be talking about register 1C and register 1B. This is the configuration for the accelerometer and for the gyro. All right, we discussed this in terms of some examples, and so that those examples will be demonstrated by her. So she will momentarily give this as an example setup where she has a register set at 68. That turns out to be the register that's handling it turns out to be the address of the sensor. And then there's a register 6B here. And register 6B is used for general things like turning the power on and things like that. The computer engineers are more adept at looking at the actual software. So again, the 1B here is set here. So this is where we can, the register that I just talked about. So I can set the gyro to full scale. The register 1C is working with the accelerometer. I just talked about those just 30 seconds ago. And then 6B is again used to set the sleep register to 0 to make sure that things run. So again, if you're an electrical engineer, don't worry about this. This is all done in the Simulink graphical user interface. For the computer engineers, you love this stuff, so just remember the pink, the green, and the yellow as we talk through this example. So let's go ahead and see how she handles this, going back to the video. And I think in this particular case, I'll make it full screen, give you the full effect here.
My next demo is I2C interface to MPU 6050 triple axis accelerometer and gyroscope.
Now, actually, before she talks too far, I keep on interrupting her, but I want to make sure you understand this setup here is going to be simplified for you. Notice that the connections between the MPU 6050 and the Mega, or the Do, which has almost the same pin configuration, is simply 4 wires. 5 volts, ground, and then SDA and SCL are associated with the I2C communication protocol. All right, those 4 connections are essentially these 4 connections here. So we are going to provide you a cable and a end piece that will allow you just to put the MPU 6050 right on the end of that cable, and you will not need to use this board.
The MPU 6050 is a 6-axis motion tracking device that combines a 3-axis gyroscope, 3-axis accelerometer, and a digital motion processor. It contains 3 16-bit ADCs for digitizing the gyroscope outputs as well as for digitizing the accelerometer outputs. I will be communicating to the sensor through I2C. I will show you how to work with the accelerometer unit. The first thing we need to do is sensor configuration. This is something which only needs to run once. Hence, I have made the following arrangement.
Now you download this from the Simulink hardware package, and then you double click in here and you set this up. You'll need to find this element, and this is a constant input, and this is a delay. So you'll need to build this, and it's done, as she explains, it's only used one time for initialization. After that, the regular hardware is used.
This is a delay block. The initial condition is set to 1. The input to this block is 0. And the output from this block goes to an enabled subsystem block. Hence, after the first sample time, the input to the enabled subsystem block would become 0, and this will no longer be enabled. Inside the enabled subsystem block, I have configured 2 of my registers. The first is a power management register. The address of this is as follows. The first is the address of the sensor. The power register allows the user to configure the power mode and the clock source. I have set the input to this register as 0. 0 means that I am using the internal 8 MHz clock on the sensor.
Okay, so you will now next have to construct these. These are dropped down by the are taken from the Simulink hardware package. I believe the enable subsystem is not from the Arduino hardware package. I think that comes from someplace else. I don't remember where it is, so I correct myself on that. Let's go and continue. If you follow this every step of the way, you will have a working subsystem. So you might as well just play what I'm doing here, and it'll work.
The next register that I have configured is the accel config register. This is the register address. I have set the range of my accelerometer through this to -2G to +2G. The command for this is 0.
Now, before she goes any too far, remember what the registers she just discussed. It was a register 1C. This is because there's 1C here, which you don't need to know about. But if I go back to this register information here, this is register 1C. So therefore, she's only configuring the accelerometer. You're going to have to, of course, you're going to finish this and you're going to get that to work. Then you're going to have to repeat this entire process again using this register here, 1B. So therefore, you would not touch the initialization blocks, but you will build another subsystem that's identical to the one that she's demonstrating. In this case, you would use register 1B. Then you'll have a working gyro. So you'll have the initialization on the top, the accelerometer in the middle, and the gyro on the bottom.
Now, coming back to the main model, I will be reading data from the accelerometer data register. This is the address of the register. The following is the format of the data that I will be reading.
Okay, so what was register 3B? In our discussion earlier, it was, again, from the computer engineering point of view, the register 3B was this one, and it was associated with taking the data XYZ. Again, you don't need to know anything about this, but there are a few computer engineers in our class, and they just eat this stuff up.
Internally, the sensor has 16-bit ADCs for the accelerometer unit. This means that the output will be in the range -32768 to 32768. That is an int16 number. Internally, there are three 16-bit ADCs for the 3 axes. Hence, I am expecting 3 int16 outputs. Hence, I have used a demux. The 3 outputs from this demux are the data of the x-axis, the y-axis, and the z-axis. You can also connect outputs to log your signal. Now, we expect an int16 output data type. Since the I2C read block only has uint8 and uint16 as the data type options, we can connect a data type conversion block and set the data type as int16.
Notice the 3B here, indicating the register associated with the accelerometer. Everything that you see here in this area, once the screen disappears, you will have to duplicate it once again. For the gyro, using register 1B, and the gyro data, instead of 3B, it would be number 43. So that is giving away everything here to you so you can get this project done.
So let us do that. Let us add a data type conversion block. Set the value of the data type in it as int16. Let us add it here.
One student said this was not necessary, but
we can now run our model.
You can verify it. If that's true.
Since the maximum acceleration value is set to 2g and int16 has a limit of around 30,000, the value of 1g will correspond to half of this, that is around 16,000. We can observe this by simply moving our sensor.
Now, she's going to do a little demonstration here. Now, how did she come up with 32,000? Well, that is the 8-bit. The data is associated with 2 8-bit bytes. So that works out to be a number of 32,000, I believe. Let's go ahead and finish this off now.
We will keep our sensor still and point the axis in the up and the down direction. Then the only acceleration that the sensor would sense would be due to gravity pulling it down. Let us try moving the x-axis.
Now, just remember how this works. As I explained last time, the soldering that you see over here is in the direction of y. Okay, so orthogonal to that is x, and z is pointing up and down. So gravity is coming down from the z direction, so it's coming, essentially, you're looking at the screen now, it's coming from your eyes down there. The only acceleration that this unit can pick up is unless you put it into a test machine, is gravity. So right now, the only sensor that can pick up the only component of the acceleration sensor that can pick this up is the z component. So if she starts dealing with the x, you're going to get 0. All right, not until she turns that x-axis and flips this printed circuit board vertically up so it points into the z direction, will you get gravity. So pay attention to this and then watch this move between 0 and now she did a scaling, so I believe 16,000 is going to be up here and negative 16,000 is going to be down here. So she kind of scaled this already. So it was representing accurately 2g, 1g, 0g, minus 1g, and minus 2g. Okay?
Right now, it is parallel to the ground. Hence, it reads a value of 0. Let us now point it in the upward direction. We can see that the value is close to 16,000. Let us now point it in the downward direction. You can see that the value is close to minus 16,000. In the same way, we can also experiment with the y and the z axis. Again, you can see that the y-axis is parallel to the ground. Let us point it in the upwards direction. You can see that the value is close to 16,000. Now let us put it in the downward direction. The value is now close to minus 16,000.
Okay, so that's it. That's as far as I need to take this video. If you can do this, you have won and you've got your system working. So again, let's kind of review where you're at. So you are now looking at the final chart here, and you are flipping as you turn that component here. And you're holding it arbitrarily in space, and you're moving it around, so you're getting acceleration and omega. This is handheld at this point in time. That's why it's not zeroed. Okay, so as you hold it in your hand and then you flip between the x and the y, you'll get different readings, and at the time that you make the switch, it changes. So I've discussed the kind of switches that you should be using. I discussed how to build this and this system. This system here is going to use the 1C register. This one here is going to use, this one here is using the 1C register. This one's using the gyro register, which is 1B, and then there's the data registers associated with that, which are 3B for the accelerometer and 43 for the gyro, all in hex. Okay, so I believe that you can set this up pretty fast now that I've basically shown you everything that you need to do. I suggest doing the blinking of the switch if you can't get blinking of the light. If you can't get that, then you'll never do this. So blink that light and then move on to this. I think you can probably put this all together in about an hour and a half if you work on it. So that is what I wanted to talk to you about today. So this is a special edition video discussing homework number 2 to accelerate you into getting it done in a few days. If that's so, that's it from me. Have a good day.